Hello again. Welcome again at this webinar about hydrogen fires and safety. My name is Matthias van der Veire and I'm a Belgian firefighter who works at the Brussels Fire Department. And I helped along with this project about hydrogen fires. So, as we mentioned before, we are going to talk in this part about hydrogen, the properties and its risks. Well, first of all, what are we going to treat? We are going to talk about what hydrogen actually is. Then we are going to talk about what hydrogen is used for. We're going to follow that by properties of hydrogen. How are we going to store hydrogen and transport this? And we will conclude this presentation with a short summary. So first of all, what is hydrogen? Well, we have this periodic system here, and hydrogen you can find at the upper top left. Hydrogen is an atom, is an element, and it is actually the smallest element that is currently known. It is also the lightest element, and we often mistake hydrogen with hydrogen gas. In common tongue, we use the term hydrogen just as we use oxygen, but it's actually a combination of two hydrogen atoms which form the molecule hydrogen gas. So hydrogen actually, we can use this. This is a flammable gas, and if you combine it with oxygen, you get water and energy. So energy in the form of heat or energy that can be used as electricity. Vice versa, if you want to create hydrogen, we need to apply energy to water to create hydrogen gas and oxygen gas. How does this look like? Well, it's more like this one. So you have the hydrogen atoms that are bonded as a molecule. They go together with the oxygen, and then you get the water and the energy that is dissipated. What is hydrogen exactly used for? Well, we often talk about new energy sources. Well, actually, hydrogen has been around for a couple of decades already. It has been used as rocket fuel, and it is one of the most known incidents about hydrogen fires is the incident of the Hindenburg, which was a Zeppelin that was fueled by hydrogen and actually exploded or inflamed rather due to electricity in the air. Why are we going to use this new hydrogen, or why do we want to use it in these in the current technology? Well, hydrogen has a high specific energy. This means that it contains a lot of energy per unit of mass. If we compare it, for example, with diesel, diesel has about 44 megajoules per kilogram. Well, if we look at hydrogen, we have about 3 times as much energy within 1 kilogram of hydrogen. This is per kilogram, but we can also look at this by volume. And if we look at this chart, 1 kilogram of hydrogen is about 12,000 liters in volume under atmospheric pressure. If we compare that with 1 kilogram of diesel, we have about 1.2 liters of diesel. So 1 kilogram of hydrogen, we have 140 megajoules, whereas with 1 kilogram of diesel, we only have 44 megajoules. So you could say that in 1 kilogram of hydrogen, you would need 3 kilograms or 3.2 kilograms of diesel. However, if you do the calculation in liters, that would mean that for every 12,000 liters, more or less, you would need about the same equivalent of 4 liters of diesel. This may seem a little bit of abstract, but compare this to, we have the diesel, which we can contain in small milk bottles, for example. You'd only need 4, whereas for the hydrogen, you would need to have more than, you would need to have about 12 cubic meters of hydrogen to come to the same amount of energy under atmospheric pressure. So It has a very low energy density per unit of volume, but a high specific energy per kilograms. So this is actually the reason why it is not used in atmospheric conditions. So how does technology solve that problem? Well, there's actually a couple of ways. The most known ones are to compress it into a cylinder, so you have a compressed hydrogen gas. And then another way is to cool it. If you cool gases, they shrink, and you can contain them in smaller volumes. So you can also have liquid hydrogen gas, liquid hydrogen rather. If you liquefy it, if you take away the temperature or take away the heat, then you can liquefy that hydrogen and make it in a smaller volume. What is it used for? Well, most of the people think about hydrogen-propulsed cars, which is actually more or less a sort of electrical car. So there's a fuel cell in this car that changes the hydrogen via a chemical process into electricity, and then that electricity goes to a smaller battery, which is used to propulse the car. But there's actually a lot more applications about hydrogen. You can use it for energy, you can use it for to create fertilizers, you can use it to upgrade biofuel, it can be used as a transportation way, but there's also several ways of creating hydrogen. You can create it by nuclear energy, you can create it by fossil fuels, or you could create it by renewable energy. And this is actually an important thing about the green aspect, because when we think about hydrogen, it's not always this green form of energy. It's not always a zero carbon. If you use it, if it's produced by a fossil fuel, then you cannot really call it a green fuel. Sometimes it's also a residue of another project, of another process, or you could create hydrogen and then capture the CO2 to use it for something different. So this is how they categorize different kinds of hydrogen to see if it's more carbon neutral or not. Now, for us at the firefighters, this is what are we going to do with that? Well, first of all, the perception of hydrogen. Hydrogen is a flammable gas. It is colorless, odorless, so we cannot smell it. It's not really poisonous, but it can thrive away all of the oxygen, so we can suffocate in this environment. So it's not directly that it would be toxic to our bodies, but if it thrives away all of the oxygen, then we can have some problems to breathe. When we look at some other properties, for example, the buoyancy. Hydrogen, as we said already, it is the smallest element that is known. It's the density is about 14 times lower than air, which results that it rises at a speed of about 20 meters per second. It's the best buoyancy on Earth, and that means that a lot of the hydrogen is just going to dissipate in the air. If you take one of the ISO pictograms, you can see that for hydrogen, there's this cloud with an arrow that points up to the top, which means that the gas is going to go upwards. You also have this, these two arrows facing towards each other, which means that it is, this is the compressed gas version. And the top lightning bolt, that means that it's actually a combination of hydrogen and an electrical propulsed vehicle. You have something similar here for CNG, the compressed natural gas, which is also compressed. The gas rises, and then an alternative would be a diesel propulsed vehicle. So we said already that the density is very low, and that is actually valid up until a temperature of minus 251 centigrades. So if we are in the outside actually most of the undesirable effects of hydrogen are going to dissolve very quickly. We can also look at the flame properties. And for the flame properties, we need to look at this formula that we used in the beginning. So hydrogen and oxygen is a combustion equation, and that creates water and energy. To understand that, we need to actually compare that to, for example, the most easy carbohydrogen combustion reaction, which is methane with oxygen, which creates H2O, so water, and carbon dioxide. That's actually if you have a perfect combustion, if all of the methane perfectly gets mixed with air and all of the everything is burned. If we look at something that is more realistic though, we also have this little element here, carbon or soot. And it's actually due to the soot that flames are visible. Soot can radiate, can become red, become orange, become yellow, and that actually gives the color of a flame. Well, when we look at this hydrogen equation, then we can see that there's no carbon present. That actually means that flames are almost invisible. But something more important, this soot or this carbon, also due to the fact that it radiates, that is the radiative heat that you can feel when you approach a flame, which is not present in a hydrogen reaction at all. So this is one of the dangerous parts that we have in our hydrogen fires. I'll show a quick video about how you can see this difference.
Here we have the propane and hydrogen flames burning on a bright sunny day. The orange propane flame is clearly visible. The hydrogen flame is nearly invisible. But when we look at the flames through a thermal imaging camera, we can see both flames clearly. A pure hydrogen flame has low radiant heat, much less than the amount of heat radiated from the burning of conventional fuels. Now, let's do the same demonstration in the dark, at night. We are in the same location that we used in the daytime. You can see that the same landmarks are visible. In the dark, both flames are clearly visible without a thermal imaging camera.
So this video gives a small indication how the visibility of a flame, about a hydrogen flame really is. It's important to notice that you cannot see the hydrogen flame, but if something around the hydrogen flame is burning, then you will obviously, that is obviously another material that is burning, and that you might see. We can also check this difference on radiation. And well, as we said before, normally in a normal carbohydrate fire, we have about 60 to 70% of the energy that is lost by convection, and then the other 30 to 35% that is lost by radiation. And it's this radiation that we actually feel. Hydrogen fires only have convective heat and no radiation.
And I'll show you just how close we can get without it being hot. You got the top one, please. Is all my fur intact? How close was that to that flame? There you go.
So small disclaimer, do not try this at home. If you go too fast, then you will have 100% of the heat going through your hands. Another way to test this is actually to approach it with a flammable material. So, as we said before, the flames can become visible if an object around it is burning. So here you see this broomstick. As soon as it is into the hydrogen flame, the broomstick inflames as well. When we look at the ignition properties, then hydrogen is also a particular interesting element to talk about, because the flammability limits are actually from 4 to 75%. That is a very large envelope for flammability limits. If we compare that to methane, which is between 5 and 15%, that is actually a very much larger flammable envelope. The detonation limits are a little bit smaller, so what's the difference between flammability and detonation? As soon as you have a detonation, you also have a pressure wave that is followed by it. The ignition, the auto-ignition temperature, or the temperature where hydrogen inflames by itself, is 510 centigrades. But the flash point, the temperature at which a gas ignites if you apply an external source, is already at minus 253 degrees centigrades. The minimum ignition temperature is about 0.017 millijoules, but that doesn't really tell us a lot. If you compare that, however, to a sweater, removing a sweater and you have a small spark, then you can already have up to 10 to 20 millijoules. So you don't really need a lot of energy to create a spark with a hydrogen flame. Storage and transportation. So we already talked about this. There's generally two ways of transportation that are commonly used right now. So you have either a compressed gas. So you compress the hydrogen, so you have a lot more of this mass into one certain volume. Generally, the pressures are between 200 and 300 bars, but vehicles can even go up to 700 bars. If we compare that, the second way is to really cool it down so the hydrogen liquefies. And that happens at minus 253 degrees centigrades. Operationally, you can actually recognize those as well. In Europe, we have the ADR conventions. So when we look at the compressed gas at 23, which indicates a flammable gas, if we look at the 22.3, then we have a very cold gas that can ignite that is flammable. So when we look at the compressed, let's first look at the compressed hydrogen gas. If one of these pressure vessels is heated, then the pressure can arise again. Heated gases increase in pressure, but the problem is that these vessels have a certain amount of pressure that they can handle before they rupture. So increase the heat too much and you may actually have a physical explosion. One of the solutions that has been designed by the Technological Society is a TPRD, or a thermal pressure release device. Or another way to deal with this is to use a composite vessel that acts with resins. More about this later. This is a new technology that is being studied right now. So first off, a TPRD, thermal pressure release device. So the words say it already. It's a thermal device. It releases pressure. So if this device gets too hot, then it will actually open up a valve. It works actually a bit like a sprinkler head, where a glass bulb can break, and then as soon as it's broken, it continues to release this gas. It opens at a temperature of about 110 degrees centigrade, and once it is open, it keeps blowing off. So it blows off often at an angled way, either upwards or downwards. There's no real conventions about this, so you always have to take care and be aware of where you can find this hydrogen jet flame. So always look with your thermal imaging camera to really know where the jet flame is happening. A second way of dealing or preventing explosions rather is to use composite vessels with a sort of resin in it. So what happens if you engulf this with a flame, the pressure will release, and this resin, this inner layer of resin, will actually start to melt and create tiny micro leaks. So actually you create a sort of porous vessel. The hydrogen can escape this vessel as soon as the micro leaks are large enough. So right now you see that the pressure is increasing, and as soon as enough of this resin is melted, you will see that the pressure will slowly release. So at this moment, the leak starts. So actually you're going to create a higher heat release rate as well, because the hydrogen is leaking from the vessel itself. So it will actually make a larger fire, but at least we will prevent explosions. So the pressure will decrease in this experiment, and then at 10 minutes, it will be engulfed with a real fire, well, with an additional fire. So imagine this, you have a local fire around the cylinder in your car, and at a certain amount of time, the whole car is involved in flames, or the whole filling station, or whatever is burning around it. So you have a higher heat release rate again. You see that the pressure is rising again. But just as before, as soon as the heat is large enough, you will create bigger micro leaks that will release the gas again at a small and slow way. It's important to notice, to make the remark that this is a fairly new technology, and recently there was actually there have been explosions of these types of vessels, but more research is needed about this. We also can transport hydrogen by cooling it down as a cryogenic liquid. Typically you use thermal insulated vessels for that, but this is very expensive and difficult to build. It's also very energy demanding. But for us, operational, as soon as we encounter one of these vessels, we have to be aware of the additional risk to have cryogenic burns. So even if the gas is not burning already, you can actually burn yourself by approaching to the cold. For freight traffic, for the compressed gas, typically this is done by cylinders. You have, well, in Europe they are limited to 40 tons. You have metal cylinders, composite cylinders. But one important aspect is that generally on these cylinders you don't have a TPRD. Typically if they are metal, then we also need to be aware, because it won't have this resin inner layer. So these bottles can actually explode. In the US, there are even these larger cylinders that can actually send up to 600 kilograms of hydrogen per cylinder. So this is an even higher risk. When we compare that with cryogenic liquids, you typically have these tankers between 30,000 and 60,000 liters, which transport about 4,000 kilograms of hydrogen. But as we said before, it's an energy demanding and an expensive way to transport this, so it is generally used for longer distances. Finally, another way of transportation is also by the use of pipelines. So Europe is actually trying to use its current pipelines to transport hydrogen as well. And in Belgium, we actually have these type of action cards or procedures, which we already used for methane gases or other flammable gases, which we implemented, which we adapted for the use of hydrogen. I'm well aware that not everyone may know these types of cards, and I'm also apologizing because it is in Dutch. But generally, we have two different options. Either it's a gas that is on fire, or it's an unignited gas that is released. We also make the distinction between a small leak, generally 10% of a leakage, and then a large guillotine rupture where a huge amount of gas or a huge amount of flames are released. And then we always create 3 different zones. So you have the house burning distance, in which people cannot be in their houses because the houses may burn themselves as well. Then we have a second zone where we ask people to shelter. And then at the third zone, we try to evacuate these peoples. And obviously, we try to do this step by step to save all these people and to deal with the incident itself. Obviously, there are a lot more technologies that involve hydrogen, which we have not covered in this webinar. So you have train transport, you have forklifts, you have filling stations, boats, and in the future there will most likely be more technologies available for this. Finally, I want to address you again to the HiResponder website. At the HiResponder website, you will find a lot of materials, such as all of the information that we are trying to condense here in a couple of minutes, hours. But there's also this e-laboratory. So if you go by the QR code, or you just use the website over here, then you can go to an e-laboratory. And the e-laboratory gives you the opportunity to work with all kinds of different properties about the bottles, about the orifices of the gas, the pressure that a cylinder can have. And to show you, for example, the flame length or the jet flame, the distance, or even explosion distances. As first responders, we really liked this information from the science community, but we preferred, however, to have something simple, because on the terrain, most first responders will know that there's no time to do these calculations, at least not in the first minutes. So we need to have these first actions, these first reactive distances to deal with. So this you can also find in the course materials. To conclude this first part about the hydrogen risks, well, first of all, realize that hydrogen is a lot lighter than air. So if you're outside of the environment, you know that most of the problems are going to dissipate themselves. If you're inside of, if you're in a closed area, do know that this will go to the ceiling. For the operational part, this will follow in the second part, but know that your basic actions about flammable gases stay put. Operationally, hydrogen flames have no carbon, so that means that it's almost invisible by day, and even more important for a safety aspect, you don't feel it until you are actually into the flame itself. So always use a thermal imaging camera to approach these type of fires. And mostly you will not know before you turn up to an incident that you will actually have a hydrogen fire. So use your thermal imaging camera at every fire where you suspect that you can have hydrogen. And then lastly, search for the TPRD, because that is actually going to show you where the gases are going to release. And be aware that you can have an explosive environment. So use a multi-gas meter, which can help you detect where you can find, in what kind of environment that you are. More about this in the operational manual. I hope that this was valuable for you, and thank you for your attention.